Okay. So is 4 meter long bar, okay, and it has a cross section T as shown in the figure below, and it's saying material Young modulus. Young modulus mean E, value of E is given, and compressive yield strength is given. Both are 260 gigapascal. And it's saying calculate buckling load of the strut if both end hinge. Hinge mean both end pin. You have to figure out buckling load. That means you have to figure out P critical. And it says solve part A. You need to solve this one if one end of the strut is fixed and the other end free. And also length is 1 meter. That means length is sense, C value also sense. Okay. Now how we can solve it? At first you look what data is given. So end condition in both cases is given. It's saying for A, C will be 1. Both end is hinge or pin, same thing. And condition B, one end fixed, other end free. So one end fixed and one end free. Condition is right over here. That means this C equal to 1 by 4. So you got the value of C for both cases. And length for part A, length is 4 meter. But for part B, length is 1 meter. Now, how you going to solve it? At first, you need to figure out the value of L by rho critical, right? That means you need to know that is a short column or it is a long column. How do you know? By critical slenderness ratio, you need to figure out by L by K critical. That I mentioned over here in the bottom. So you need to figure out L by K critical. Then you can say if your L by K is less than this value, then it will be Johnson equation. Is higher than this value, then it will be Euler equation. Then you need to figure out rho or K. What is rho or K? K equal to, that K equal to square root. That means root over of I minimum. That means minimum value of I divided by cross-sectional area. That is the L or rho. And L by critical, we already have the formula. So you see, you need to figure out the cross-sectional area, then you need to figure out Ixx, then you need to figure out Iyy. Then you need to figure out I minimum. Okay. Now, since this cross-section is not complex, I am not giving value of I. You need to figure out how you solve this problem. But if cross-section is complex, then I might give you the value of I, 0.0034. For example, I can give you the value of Y, say 0.1.23 millimeter 4 or meter 4. Then you figure out the I minimum. But in this case, we need to figure out the value of I. So let's see how we can solve this problem. Just 1 second. Share. Okay, very simple problem. I didn't put the question over here. At first, you'll figure out what data is given. Number one thing, for part A, L equal to 4 meters. The length of the column is 4 meters. For pin support or hinge support, C equal to what? Now, you need to know the compressive yield strength of the material. So, if I go for new share again, you see modulus is given, value of E is given, and compressive yield strength also given. Why we need compressive yield strength? Because we need to figure out the critical slenderness ratio. And here is the formula for critical slenderness ratio. 1 second, right over here. So we need to have value of E in condition and also sigma Y. Sigma Y, that means compressive yield strength. And modulus of elasticity also, that will be compressive yield strength. So in this question, it's saying compressive is already given. So you can use it directly, right? But compressive is given. But if I give you value of, I'm saying the material has compressive Young modulus this much, tensile Young modulus this much, then I might say tensile yield strength 260 and compressive yield strength 100. So in that case, when you, since you are working with the column, you need to use the compressive property. So we need sigma Y. Sometimes some book, instead of sigma, they use Fy or FTY, FCY. Some book use SY. That we already discussed earlier. Okay. So I'll go back to the previous slide where we are solving this problem. So I say compressive yield strength, FCY or SY, you can write sigma Y is the same thing, equal to 60 gigapascal. Convert in Pascal, then modulus of elasticity 200 gigapascal, then you convert in Pascal. Now, part A, it's saying both end is hinged, and part B, you need to figure out P critical. If length of the column is 1 meter and one end free, other end fixed. Okay. So you see, to figure out L by K critical, we need to figure out the I. Without calculation of I, you cannot do anything. Also, you need to figure out the area of the cross section. So area you can easily figure out. You just divide the cross section area by 2 segments, right? So I figure out area is this much millimeter square. Then convert it in meter square. Okay. Now I need to figure out the value of YCG. Why YCG? You see, this cross section is not symmetric. This is a T right over here, like that, right? So this cross section, the symmetric or vertical axis. That means what I like to say, area on the left side, right side is same. But vertically it is not symmetric. That means it is not symmetric along x-axis. Upper has a more area, lower has a less area. So in that case, the I we use in the column, that is respect to CG of the cross section. So we need to know where is the CG of this object, okay, of this cross section. So how we can figure out the CG? So this is our cross section. It has all the geometry. So obviously you see CG, you will know that it will be along on this line because vertically it is symmetrical. But now CG will be where? It will be here, or it will be here, or it will be here. We don't know. So that's how we need to figure out. But it will be close to upper flange because the upper portion has more area. Now we need to figure out the YCG. And you see, we'll apply the formula from engineering mechanics. YCG equal to sum of area into YCG divided by sum of area. So you see there is a, you take the top area 150 into 20. 150 into 20. What will be his CG? His CG will be around right over here, the middle, right? So what is the distance from the bottom? This is total distance from here to here is 120, right? 120. Then what will be distance from this CG to this one? So obviously this distance is 10 only. So 120 minus 10, 110. So 110 is the CG, area into CG that we put right over here, area into CG. Now you take the bottom one. You take the bottom one, what is the area? This distance is 100 by 20, 100 into 20. So it's 100 into 20 is the area. And where will be the location of CG? So location of CG will be at the middle of this height, right? This is 100, so it will be right over here. So you put area into YCG, area YCG is 50, divided by sum of area, 2 area. So we are getting 86 millimeter is the YCG. 86 millimeter from where? 86 millimeter from the bottom. So if you look the bottom figure, we found right over here 86 CG. Now you need to figure out YCG and I'm sorry, a moment of inertia along x-axis and along y-axis. So how you can figure out? You see, it is not a kind of box. So what I did, you can calculate different way, but I divide this one. I took this 2 area and I apply this formula that I, respect to CG of the any point, will be equal to I dot CG. That means moment of inertia of that cross section or area respect to his CG plus area of the area, which one you are calculating, that area into d square. What is d square? Distance between CG of the area into CG of the area whole square. So d is the distance between 2 CG. One CG is the CG of the area, other one for which point you like to figure out the inertia. Okay, so you see, we have to figure out the inertia respect to CG of the cross section. YCG. See, the whole YCG is right over here. Okay. So what will be the XCG? This is YCG. So you are getting height from here to here. This is the YCG, right? Then what will be the XCG? XCG will be half of this length because it is symmetric along vertical axis. Okay. Now, I like to figure out the moment of inertia of full cross section with respect to this CG. So you work by one by one. So how we going to work? At first we are thinking, we are taking this upper area. So you take the upper area along x-axis. What will be the 1 by 12 BH cube? What will be the B? B will be 150, H will be 20, right? So you see, we put 1 by 12, B 150 millimeter, that means 0.15. H 20 millimeter, that means 0.02 square. This CG, you are getting respect to CG of this area, not respect to this point, but we need to figure out respect to this point. So what we need to do? A d square. So what is the area? 0.5 into 0.20. This is the area of this part. Into d square. What is the d? So which d you will take? D mean distance from here to here. So what is the distance from here to here? 86. That means from here to here is 86. Okay. So 100 minus 86. What will be from here to here? 14. And from to here, half of 20, 10. So 24. So AD square. That's why I put 0.024 whole square. So this area, we are taking only the upper portion, right? Only this area we already got. Now we need to figure out the bottom area. So bottom area again 1 by 12 BS cube. So 1 by 12, right over here 1 by 12. Over here it will be a cross sign. I forgot to bring the cross sign. Okay. Now, so right here we can bring the cross sign instead of dot. So 1 by 12 BS cube. Which one is the B now? We are talking about the this area. So instead of B is 20 and H will be 100. So that's how we are getting 1 by 12 BH cube. So you are getting this inertia respect to which point? That means we have upper portion, this one, we already got it, and lower portion is this one. So this mass inertia, you are getting respect to CG of this vertical portion. But what is our CG of the whole body? Right over here. That means it will be around right over here. Okay. So we need to figure out respect to this point, but we by 1 by 12 we are getting respect to this point. How can we make correction? A plus d square. So right over here, what will be the area? Area is this one is area will be this one. So it's a d square. So area is 0.10. Okay. So this one you see, what is the area of this one? 100 millimeter, 1.1, 20 millimeter, 0.02 into d square. So how much will be d square? You see distance from here to here is 86. We already got it right up, 86. And what is the distance from here to here? Should be 50, right? Because half of 100. So 50 minus 86. So from here to here is 86. 1 second. Only 86. That we already figure out with formula. And this portion is 50. Then how was this portion? From here to here. Then 86 minus 50. That means 36. So 0.06 whole square. So we got the IXX. Similarly, we need to figure out IYY. Then we'll get the I minimum. Now, how we can figure out IYY? You see, similarly, we can figure out the two area, upper and top. So 1 by 12 BH cube. Here is 1 by 12. What is the B? 20. What is the A is 150. Okay. Then plus AD square, because this is given with respect to this point, right? So we are figuring out IYY. That means if this one y-axis along this direction, let me take arrow. So this is y-axis along this direction, x-axis. So in that case, right over here, a d square, but your d square will be 0 because along x-axis, distance between this point, I'm talking about distance between this point and this point, horizontal distance, how much? 0. Along x-axis, their distance is 0. So it will be a d square. So d will be 0. That's why I didn't put the second term. I just put the first term. Now you take the bottom one, 1 by 12 b h cube. Same thing, in that case, b will be 100, 1 by 12 b, h will be 20. Okay. Now, what will be the CG for this area? CG will be right over here, right? Again, along x direction, both are in the same line. So d is 0. So this is your IYY. So we have IXX, we have IYY. Then we need to figure out which one is minimum. So obviously you see IYY is minimum. So I minimum equal to, I put minimum IXX into IY. So it will automatically give me result. But in your case, you can look thus to figure. You say between IX and IYY, I minimum value equal to this much. Like that. Okay. Now we figure out the value of K or rho equal to I minimum by area. This is K or rho. Okay. Then you figure out value of L by K. What is our L? L is given 4 meter. That we already put it right over here, 4 meter. So then you do L by K. So L by K equal to this much. Now, you don't know that this is the left side or right side. So you figure out L by K critical. Now, I just put L by K critical equal to SR, just one factor. But when you calculate, you can easily figure out that L by critical equal to this one, this value. Then we figure out the value. SY mean sigma Y. E value is given. N condition, pin to pin 1. So I got critical slenderness ratio 8. But right over here, ratio is 118. So it will be a short column or long column. Anyone? Anyone?
Column, sir.
I'm sorry?
Sir, long column.
Long column, good. Your ID?
131.
131. Okay, hold on, let me write down your ID. So it is long column. So if it is long column, then which equation we can use? Obviously, we can use the Euler equation. Okay, then you say slenderness ratio L by K greater than L by K critical. This is our Euler equation. From here, you just figure out the P critical. All the values given in the already we mentioned. You see, right over here, there is no P critical. Over here, you will use the your slenderness ratio. And P critical, L by K critical is actually a tool like a scale or hammer. Say with hammer, you are testing a brick, that it is a number 1 brick or number 3 brick. So that one is L by K critical. To test whether it is a short column or it is a long column. So I got this much Newton, convert in kilonewton. Okay. Now second part will be same problem, but they're saying N condition 1 N free, 1 N fixed. That means fixed free N condition. So C value equal to 1 by 4. Okay. And length of the column is 1 meter. So what need to do? You need to figure out again slenderness ratio. So your critical slenderness ratio, your L by rho is 29, and critical slenderness ratio coming 4. What does it mean? Still it is right side, right? Our value 29.6, but critical is only at this point, value is only 4. So that means again you need to use the Euler equation of column. But if you are in the left side, then you need to use Johnson equation, like we solved one problem in the last class. So similarly, you solve, you got this first. So what you see over here, that if column length is decreased, right over here, load taking how much? 72 kilonewton. And right over here, it is taking 2800 kilonewton. So what makes the difference over here? column make shorter, that means it should carry more load. But what is the difference over here? Why it carrying less load? Reason is the end condition, because in previous problem, end condition was 1, but right over here, end condition is 0.25. Okay. So this problem I put it to understand the effect of end condition and the length. Okay. Now we will talk about something else, that how we can solve a problem if a load applied in the column is not going through the cross section of the column. Then number 3, same problem. It's a column is made of aluminum extrusion like this one, and it's saying Z-shaped bar. That means cross section is like a Z, letter Z. Find the allowable buckling stress. That means sigma critical you need to figure out, and load. That means P critical. You figure out P critical, multiply by A, you got the sigma critical. First you can figure out, then multiply by area, you get the load. Now it's a support is pin to pin, and you need to figure out for length 26 inch, then you need to figure out for length 16 inch. And FCY, that means sigma Y is given 70 KSI, and EC is given 10.7 into 10 to the power 6, and this is the material. Since this is a little bit complex cross section, so I give you the value of that. This is the area, this is the IXX, and this is the IYY. So in our case, this will be minimum, right? Then you just figure out it's a short column or long column. Then you use either Euler formula or Johnson formula, and you need to figure out the value of C. C it's saying already that pin to pin support. Okay. And length given 26 inch and 16. So you'll solve by yourself this one. And now we will use something else. Right over here, the two formula so far we learned. Johnson formula, other one is the Euler formula. In both cases, load is go through the CG of the cross section. So both cases, load is going this location through this location. Okay. Now, if load is not going through the CG, then how we can we'll calculate the column load or buckling stress. So you see in the line in this figure, load is applied right over here. Okay. So this much distance from CG to load point, this much distance, that means distance from this point to this point is called eccentricity. So we need to see that what will be effect if there is a eccentricity in the column. So you see this one, this figure, we can have a simplified view from here to here. How? This is the CG. I'm making the CG line. This is my CG. Then this is the extended portion. I'm saying this portion is extended. That means this one I can simplify it like a body, a bar. His CG is right over here. Right over here. That means CG going through this line, but load applied a little bit far away. What is the distance? Distance is A. And now in that case, how we can do the trace analysis, or how we can figure out the critical stress in the column. So you see right over here, this value of E. What is the effect of eccentricity? And from outside, you can see only load P, right? But internally, how much load is there, or how many type of load is working, you cannot say. We see the load from the external load, but we are able not to see the internal load. So what I like to do, In this P, I like to see how much internal load actually working at this point. So how we can do it? So what I did, I cut this portion. This portion means this portion from the main column. So I cut it from this portion. So I will get this one, right? This line. Then this how much force working? Right over here, force working is P. So I like to see how much force working over here. If I got point how much force working over here, I can figure out that how much force working right over here, right? And you can figure out. So how we can make free body, stabilize this body. What is the distance between this point to this point? Distance is E, eccentricity. Okay. Now, this force working upward, then this will be working downward, right? That I can make the free body. Now, is it balanced? Anyone? Is it balanced?
Yes, sir.
Look carefully.
No, sir. No, sir.
No, sir. Why no?
It will have a movement, sir. Opposite direction, sir.
Because it is rotating clockwise, anti-clockwise direction, right?
Yes, sir.
So that's why it rotating anti-clockwise. So you need to put a bending moment along this direction. Okay, that's I did over this same figure I put over here. So initially my column was like some sort of straight line like that, right? So this portion I took on. I make feasibility. So what will be my load over here? Easily I can show that what I like to say. Yeah. So I got the load if at line, if I let me draw a line. I'm saying if I say this is our column, from here we have extension part, right over here extension part. So if I say this is point A, this is point B. So at point B, this load is working. So I like to make the free body of line AB. So this is my line AB. This is the point B. This is the point A. Right? Now, how much load working within this column? Like at this point. This is also A, the common point, right? How much? Obviously, this force will be opposite of this end, right over here. You see, I make free body, this P, so right over here, this P working downward, so over here, this will be upward. This is anti-clockwise, so this will be, sorry, this is clockwise, so this will be anti-clockwise. So right over here, we will have a force. If I make a line with red color, that we will have one force upward direction because this is working downward. So this is P. And also working a bending moment opposite of this one. This one clockwise, so bending moment will be anti-clockwise. M. So it's P and right over here M. This P and M you cannot see on your eye. So that means this load are the internal load. Now, how we can figure out the value of this bending moment? How can we figure out? You just take moment over here. You take moment over here. If you say anti-clockwise is positive, you are saying anti-clockwise positive. You take moment over here, then you are getting P into E, rotating anti-clockwise, right? So P into E, okay. And this one is clockwise, then this will be minus M. minus m equal to 0. So what is m? So m equal to p.
P into E.
P into e. This is the value that I figure out right over here. Okay. Now, so instead of showing this load, I'm showing load over here. You see, this way, you can transfer load from one point to another point. Okay. Now, I can say that with this condition, this beam is bending like that. So if I say vertical axis is y, or vertical axis, I think they put x, and along this direction is y, then if I cut it right over here, I'd like to see how much force is working right over here. Okay. Could you hold on 1 second? The people making noise. Okay, I'm back. So, are you able to hear me? Hello?
Yes, sir.
Okay. So,
Yes, sir.
we like to figure out that how many force working right at this point. How we can figure out. So, showing over here, we will cut it right over here. Okay. So, you cut it right over here. I cut it, right? So, if I start from the cross, that means I don't have nothing. I have the bottom this end. So bottom this end, I have this one force working upward. Okay. And what is the other force right over here? Other force is working is M. And what is the value? This M? P into E. So I can say right over here, there is this bending moment. So this is P. And over here, bending moment M equal to P into E. I'm just putting P into E. E. Okay. Okay. Now, what is my target? And my target, how much force is working right over here? So vertical force, this is working upward. So there will be one downward force, reaction force, right? And is balanced now? Is it balanced? Obviously, no. Because you see, even you forgot about this moment, that this moment equal to P into E, right? Let me write down a little bit clearly. This moment equal to P into E. So if this moment P into E, and also you see this was working along upward this direction, and this one downward direction. So these two also rotating clockwise, anti-clockwise. This one PE also rotating anti-clockwise, and these two forces also try to rotate the body. That means what I like to say, that there should be a bending moment right over here. So both are try to rotate this column anti-clockwise. So there will be one bending right over here. It's clockwise bending. And how will you figure out that bending? You take moment over here. You take moment, say this moment is M. So if I say, if I take the moment, I am saying clockwise plus, mean positive. Okay, then what are you getting? You right over here. So you have this one, P into this distance. So if this distance is Y, then I can say P into Y. And this one actually rotating anti-clockwise, right? So this will be minus, because they are rotating anti-clockwise. I was saying clockwise positive. Then you have one more moment, P into this distance, that is Y, into PE. So this one also minus P into E. Plus, you will have this one, this M. So I am saying this M equal to 0. So from there, you can figure out the value of M. Okay. That is our target. We need to figure out the value of m. But what I did, if you look in the clearly in the figure, this moment I put in opposite direction. I put intentionally, not I put in the all the book or who were derived the equation for the column, because it make the easier to solve the differential equation. So our value will be only negative. Right over here, our value is coming m equal to p into y plus e, right? So right over here, I can say moment m. Let me take the test. So m equal to p into e plus y. This will be our equation. But I put opposite sign. That means over here only will have a negative. So let's go back to previous space and getting this bending moment. Mx equal to p into e. And why is a mx? Because this moment, this amount will vary the location of the x. X is 0, e over here, right? Mx will be equal to pe. Then x equal to L, you have moment right over here. So that's why they put mx. Now, our Euler-Bernoulli equation for the beam or column, we have this one. Now, this mx value you put over here, this equation. Then finally, you get this equation. Okay. And now this equation, you can simplify a little bit. This value you can bring it left side, and p by e, you can say like that, root over. In the last, in case of Euler equation, we put value k equal to root over something, right? But right over here, you can keep it same. You see, this is a constant. P by ei also a constant. Right over here, only e remains outside. Now, if you solve this differential equation, then you need the boundary condition. Now, what is the boundary condition? You look this figure, you see, if x equal to 0, then y equal to 0. Y 0 means along this direction there is no deflection at point x equal to 0. Similarly, if x equal to L, right over here along y direction there is no deflection. So right over here is a mistake. It should be over here 0. So x equal to 0, y value 0. X equal to L, y value also 0. Then you solve this differential equation, you get y equal to this one. Okay, by applying this boundary condition. Since this is not math class, so we are not showing this how the math, how you solve it, but we are saying we apply this boundary condition, we get this is solution of y. Now, what is our target? Our target to figure out the stress. But how you can figure out the stress? We got only deflection of y, not the stress, right? But if you look carefully, right, this point, this beam or column subject to harmony load. Number P is the axial compression load. That means P is the compressive stress. And M actually is the bending stress. So what does it mean when there is a eccentricity in the column, then there will be stress like sigma equal to number 1 stress, compressive stress, direct P by A. Other one you have bending stress. So what is the bending stress formula? M star C or Y divided by I. Right? Because in this column, there is 2 load working, not 1 load. Other thing right over here, what they did, we got the equation of right over here, y, right? What is y? Y is the lateral deflection. And when y will be maximum? if x equal to L by 2. At the middle, lateral deflection is the maximum. So if you put x equal to L by 2, then you use the trigonometry and rearrange the formula, then you get delta. What is the delta? Delta means lateral deflection when or value of y when L equal to L by 2 or x equal to L by 2. That means at the middle of the beam. So in that case, we got this formula. So at the middle, what will be the bending? You look, our bending as x, location x, we already found this much, that P into EY, P into EY. You right over here is the distance y, but at the middle, what is the distance? Delta. So moment will be minus P star E into delta. Okay. So they are saying maximum moment we are getting right over here, P into delta. Now, delta value, we already got it over here, right? You see, is it possible to figure out the value of delta from this top equation? We can figure out this value. Delta plus E equal to how much, you see. You can figure out if you multiply both sides with the E, then what are you getting? E into this value. You are getting this value minus E. This minus E, you bring left side. So you get E plus delta. You get E plus delta equal to this value. Then you multiply the P. So this is the maximum moment working at the middle of the column. Now, what is our stress? Our stress in the column is, okay, do we have time? We have time?
Sir, no, sir.
How long? What time
Sir,
is
the
our
time has already finished.
Time's up,
We have
sir.
taken 5 minutes.
Time's up.
Oh, I take already 5 minutes more. Okay, just let me finish this slide. Okay.
Yes, sir. Yes.
Okay.
So we have formula that, you know, right this point, there is a two force working. One is bending, other one is direct compression. So for direct compression, what will be the stress? P by A, right? Axial member. And for bending, it will be MC over I. And look carefully. This C is not the end condition. This C is coming from where? It's coming from your beam. Because in the beam, normally you write down sigma equal to MC over I, or you see some book write down my divided by I. So what is the y and c right over here? That is the distance from the neutral axis of the beam to the outer fiber. That means if this is the cross section, and then CG will be right over here, right? Then value of C, if this is the neutral axis of the beam, then value of C will be this mass, this distance. Okay, not the end condition over here. So you need to remember. And this I we can replace it because we know K equal to I by root over A. So this I we can change it. Okay, so it comes MC plus A square. Now this P by A, we can bring over here P by A. How? This C is not the end condition, this one. Okay, this is like distance from neutral axis to the outer fiber of the column. Now value of M is right over here. So you see there is also P coming, because if this value of P, M, this M value, oh sorry. Hold on a second. If this M you put over here, right over here, then you will get a P by A. So you will see in the next time we will solve it. Just I show you the what will be solution look like. Okay. So this M will put over here. Finally, we will get this type of equation. This one. Okay, so we need to leave it over here because I have with section B at 240 again. Okay, so far any question?
Sir, on maximum moment, why there is no minus?
On maximum moment,
Yes, sir.
in the minus sign, you look, we are looking for the maximum value of the bending moment. So you see in the derivation, what is the maximum value of our we are getting? Minus P into Y, right?
Yes,
So
sir.
minus P into actually delta. You're right?
Yes,
P into
sir.
delta, because at maximum location with delta value is maximum. So P into delta, right over here, if you figure out the E into delta, then you get minus sign right over here. Okay. No, it's not my, if you ask a very good question. Right over here, I think your question why is not getting minus sign over here. Okay. I think there will be minus sign right over here. Okay. Here will, this is the mistake. There will be minus sign over here. Okay.
Okay, sir.
Without minus sign, because we figure out right over here that mx equal to p into e plus y. So there will be minus sign right over here. Over here, okay. So let me put a minus sign over here. So if you put minus sign, then there will be a bending over here. Now, there is a one question. Sigma equal to MC over I. And you ask a very good question because a column, when it is bent, then what you get? If it is bent only due to the bending moment, so say this is the column. Everybody look, and she asks a very good question. So say you are putting plus bending moment plus, then what will happen? So one side will be your tension, right? What will be the other side? Anyone?
Compression.
Compression. So this, if I say this point A, and I'm saying left side is point B. So it has a compression point A due to the bending. Then it has one more compression, that is hot, P by A, right? That means at point A, there will be two load. One will be two stress, direct stress, P by A. P by A plus there will be also compression, right? Due to the bending. So how their compression stress you will figure out. Sigma by MC over I, right? I'm putting I, this I. Now, but in the B, this is for point A. What about the B? At B, also it has direct compression, P by A, right? Then, but for bending, it is tension, no more plus sign, then you put minus. So you put sigma into MC over I by I, right?
Yes, sir.
So you see, even you put the bending moment negative over here, in that case, this formula will be negative and this will be positive. Okay.
Okay,
So
sir.
that's why they don't, once they took the only absolute value of the bending moment, because this absolute value of the bending moment is making a column on-site compression and on-site compression. And that's why it is more critical when you normally in all other industry, aerospace and shipbuilding industry, say we attach column to end, then you need to make sure that there is no eccentricity in the column. You need to avoid the eccentricity because it is heavier because it creating compressive load. Again, due to the eccentricity, again it creating one more extra compressive load. So if both add together, it makes heavier. Parts going to fail. Okay. So right over here, you can just ignore this negative sign. So your answer is clear?
Okay, sir.
Your ID?
So 131.
131. Okay, good. Thank you very much. So anyone has any question? I think I took more time, but anyone, any question? No?
No, sir.
Okay.